Hi everyone and welcome to this episode of Keipert Labs. In today's video we're going to be discussing the concept of oxidation state. So in giving you the overview, we're going to define what we mean by the oxidation state of something, go through the rules that we use to either determine or to remember what the oxidation state is for particular elements. We're going to have some practice or show you how to calculate oxidation state or the oxidation number, and then relate them back to redox reactions, which we learned about in our previous video. So defining oxidation state. So it's an innate or kind of characteristic property of a particular substance that relates to how many electrons that atom has at a given moment. So I appreciate that definition is a little nebulous or a little vague to a degree, but you'll see kind of how this plays out shortly. It's also often known as oxidation number. So those two terms are interchangeable. They're so interchangeable I even mucked up my words. But so oxidation state or oxidation number are equivalent concepts. They're always expressed in Roman numerals. What you'll see as we go through, I'll also be expressing them in terms of actual normal integers as well, just to help you get your handle on how this kind of works. And they can be either positive, negative, or zero. Okay, so they are numbers. So yeah, positive, negative, or zero. All right, now I appreciate that this table is, all of a sudden there's lots of these different things. But so a couple of key things we'll go through. Okay, so the first one is that the oxidation state for the atoms when they are as an element is always zero. So hydrogen in H2 is zero. Copper metal, zero. Silver metal, zero. Okay. The oxidation state of a monatomic ion is equal to the charge on the ion, its valency. So the oxidation state of chlorine in the chloride ion is -1, okay, because that's the charge on the ion. If it's a sodium ion, it would be +1. The oxide ion, it would be -2, and so on. The oxidation state of hydrogen in compounds is +1. The only exception is when we're talking about hydrides. Compounds where it is -1. So hydrogen in sulfuric acid, H2SO4, is +1. Hydrogen in sodium hydride is -1. Now, very rarely are we practically talking about hydrides and it being an issue. So almost every situation you'd encounter, it would be +1. Oxidation state of oxygen in compounds is -2, except in peroxide compounds where it's -1. Okay, so just same as we saw before. It's that exception to the rule. So the oxygen in sulfuric acid is -2, but the oxygen in hydrogen peroxide is -1. But again, we won't come across these very often. Okay, so by and large, it will be -2 and +1 for hydrogen. Okay, so the sum of the oxidation states of all atoms in a molecule is equal to 0. So all the oxidation states even out to be 0 in the end because the molecule is neutral overall. Okay, so we know in sulfuric acid, we know what the hydrogen is equal to. We know what each oxygen is equal to. Now, each oxygen of those four counts as -2. So all those oxygens count as -8 altogether, 4 times -2. And likewise, the hydrogens count as +2, +1 for each of them. So we'll show you how to work out the oxidation state of this in a minute. But so we're looking at this overall idea that all of these are adding up to 0. Okay, and then if we're talking about a polyatomic ion rather than a neutral molecule, the sum of all the oxidation states is equal to the charge on the ion. Okay, so all the oxidation states in phosphate add up to -3. Okay, all of them in the ammonium ion add up to +1, and nitrate is -1, and so on. Okay, so we can work out the oxidation state of something unknown based on that principle. Okay, so we're going to apply a couple of these now just so that you can see how we can use these rules to calculate oxidation state. Okay, so if we have a look at Fe3+, okay, so the charge on that ion is 3+, so therefore its oxidation state is 3. Okay, so when it's a positive Roman numeral, we're not writing plus. Okay, we will write a minus if it is minus, but in this case we're just going to write 3, so +3 in brackets as an integer. Okay, now we're thinking about the oxidation state of manganese in the permanganate ion, MnO4-. So looking at the last rule on our previous slide now, that all the oxidation states add up to being -1. Okay, so 1 manganese and plus 4 oxygens equals -1 overall. But we know that oxygen in compounds is equal to -2. So we can substitute in -2 in this situation, and then we can solve for the oxidation state of manganese, which is 7, or as a Roman numeral or as an integer. Okay, and then we can do the same thing with chromium in the dichromate ion, which is probably the most complicated example we ever come across. So what we're saying here is that 2 chromiums plus 7 oxygens equals the charge of -2. And through substituting for the oxygen, just like we did before, we can determine that the oxidation state of chromium in this ion is +6. So 6 as a Roman numeral or as an integer. Okay, now the reason that this matters to us is that not just, so it's a useful kind of skill in our chemistry tool belt, but also that the value of oxidation state tells us something really important about a redox reaction. So because we can look at the change in oxidation state as a way to signal that a redox reaction has occurred, especially that redox reactions sometimes don't seem very obvious. They don't necessarily seem like we've actually changed oxidation states. Okay, so we can look at and say, all right, it has then oxidation state increased for a substance, therefore it has oxidized, so becoming more positive for its oxidation state. Okay, so these statements in brackets here are important because they can clear up something that might not be immediately obvious. If it has decreased or become more negative in its oxidation state, it has been reduced. Okay, so because we've either taken away negative electrons or we've added more negative electrons, which changes our oxidation state. So, and likewise, if there has been no change in oxidation state, then it cannot be a redox reaction in any way. Okay, so that's important. Now, like I mentioned earlier, that these kind of principles allow us to recognize that lots of the reactions that we are familiar with actually involve electron transferring processes, even if we didn't expect that to be the case. Not just ones where we actually generate electricity from them, but others as well. We're not going to tease that out at this point, but just we can use this definition in lots of contexts. Okay, so for example, just showing how this kind of connects. If we look at oxidation number or oxidation state of iron going from iron 2+ to 3+. Okay, so the oxidation state on at the start is +2. It increases or becomes more positive to +3. So it's increased, so therefore it was an oxidation. Okay, so by identifying that, then we can look at how many electrons were being transferred as a result and then place them in our equation accordingly. We'll look at that in a subsequent video. Okay, if we look at the oxidation state or oxidation number of manganese in permanganate going to manganese 2+. Okay, so that we can see, now we worked it out before, but you could work it out fresh, that the oxidation state of manganese in permanganate is +7. Over here it's +2, so it has decreased or become more negative, so therefore it was a reduction. So to go from permanganate to manganese 2+ is a reduction process. Okay, so we've defined the concept of oxidation state or oxidation number. We talked about the rules that allow us to determine or to work out or to understand already the oxidation state of different elements in compounds or in neutral molecules. We've looked at how to calculate oxidation state for a range of different substances and seen how they connect us to redox reactions. Thanks very much for watching. Bye for now.